Hi, my name is Vincent, and this is a video on random variables, including the expected mean and standard deviation of them. A random variable is a variable whose value is subject to chance, so there's no really definite value for it at any given time. Unlike a traditional variable where you could just simply solve for it, you can't really solve for a random variable. So its real use is as a function to quantify a random process. As an example, let's define a random variable. Random variable x will equal 1 if we flip a heads with a coin, and it will equal 0 if we flip tails with a coin. That's how we just simply quantified a random process, the random process of flipping a fair coin. Coin flip is also a good example of what a discrete random variable is. A discrete random variable is one which may only take a countable number of distinct values, such as 0, 1, 2, 3, 4, on and on and on. On the other hand, we have something called a continuous random variable, which is one that can take an infinite number of possible values. One example of this would be, say, finding the exact weight of someone in Rohnert Park. There could be an infinite number of possible values. Now I will be presenting a few real-world uses for random variables. Note that from this point on in the video, I will be referring to discrete random variables as just simply random variables. For example, let's pretend that I own a company that makes electronic gadgets. 1 out of 50 gadgets is faulty, but I don't know which one is faulty until a buyer complains. So let's say that I make $3 of profit on the sale of any working gadget, but I lose $80 for every broken gadget because I have to repair it. Will I make a profit long term? The information that we were just given is called a probability model for the random variable. It's a collection of all possible values and the probabilities that they occur in. Now we can't predict what will happen, but we can say what we expect to happen. To do this, we need the probability model. The expected value is a parameter of this model. In fact, it's just the mean. We'll signify this with the notation e of x. It's very easy to calculate the expected value of a discrete random variable. You just have to multiply each possible value by the probability that it occurs in, and find the sum. Now let's see if my company can expect to make a profit in the long term. So the expected value equals the outcome times the probability that it'll happen plus another outcome and the probability that it happens. Since the expected value is positive, my company can expect to make a profit. On average, we will make a profit of $1.34 per gadget. Of course, this expected value, or mean, is not what I actually make on any particular gadget. No individual gadget will make me $1.34. We're dealing with random events here, so some gadgets will make me $3 and other gadgets will lose me $80. Because I'm running a business here, I need to anticipate this variability. I need to know the standard deviation of the random variable. For data, we calculated the standard deviation by first computing the deviation from the mean and squaring it. We do the same thing with random variables as well. So first, we find the deviation of each outcome from the expected value. Next, we square each deviation. The variance is the expected value of those squared deviations, so we multiply each by the appropriate probability and sum of those products. That gives us the variance of x. Finally, we take the square root to get the standard deviation. This comes out to about 11.62. Here is the formula for what we just did. Because these are parameters of our probability model, the variance and standard deviation can also be written as sigma squared and sigma. As we already know, my company can expect to make an average profit of $1.34 per product that we sell, with a standard deviation of $11.62. This standard deviation gives us an indication that it's not really a sure thing that I'll make a profit. There's a pretty big spread, and therefore risk, for an average profit of only $1.34. I'm going to talk more about means and variances. All of the following rules apply not only to discrete, but also continuous variables. We know that adding or subtracting a constant from data shifts the mean, but doesn't change the variance or the standard deviation. The same is true for random variables. In general, when you multiply each value of a random variable by a constant, it also multiplies the mean by the constant and the variance by the square of the constant. The mean of the sum of two random variables is the sum of the means. The mean of the difference of two random variables is the difference of the means. If the random variables are independent, the variance of their sum or difference is always the sum of the variances. Now, we're going to put together everything we've learned so far and look at continuous random variables. Continuing off the last example problem, let's say that this time I'm not worried about the expected profit, but rather I'm worried about how long it takes to pack and box each item. The company has told me that the packing stage can be described by a normal model with a mean of 12 minutes and a standard deviation of 2 minutes. And the time for the boxing stage can also be modeled by a normal model with a mean of 8 minutes and a standard deviation of 3 minutes. Now, using a normal model is a pretty common way to model events. However, what's different from last time is that we no longer have a list of discrete outcomes with their associated probabilities. Instead, we have continuous random variables that can take on any value. Now, any single value won't have a probability. For a normal random variable and any other continuous random variable, the probability that it falls within an interval is just the area under the curve over that interval. When two independent continuous random variables have normal models, so does their sum or difference. This fact is a special property of normal models and is very important. It lets us apply our knowledge of normal probabilities to questions about the sum or difference of independent random variables. Now, let's solve a few problems. What is the probability that boxing 2 units consecutively takes less than 15 minutes? So first, we define our terms, which I've already done here. And then we find the expected value, which is sort of a given, I'd say, because the expected value is the mean, so we were given the mean already. So we just add the two together. And the expected value, or the expected time in this case, contextually, is 16. And since the times are independent, you can find the variance by adding them as well. And now we take the square root of the variance to find the standard deviation. Now I can model t with a normal model with a mean of 16 and a standard deviation of 4.24. Don't forget that I can do this because both random variables follow normal models, so their sum is also normal. Now I have to find the z-score for 15 minutes. So we take the mean, which is 16, minus the z-score, 15, all over the standard deviation. Here's a picture of the normal model for the total time. I shaded the region representing less than 15 minutes. Now we can see there's a little more than 40% chance that it will take less than a total of 15 minutes to box two systems. Now, question number 2. What percentage of items will take over 25 minutes to box and pack? Now I can model t with a normal model, and then I can use a table or technology to find the probability. Again, I've made a picture of the normal model, and I found the probability. Probability is about 0.08, which means that around 8% of the time it'll take more than 25 minutes to both pack and box. So yeah, this is the end of the video now. I hope you've learned how to work with random variables, and I hope you can see how useful that they actually really are. For instance, we can use the probability model for a discrete random variable to find the expected value and the standard deviation for basically anything where you already know the probability and the outcome. So for instance, cards, dice, anything of that sort, you can know what to expect, and also you can know the variability of it. For continuous random variables that follow the normal model, well, you really see how special normal models are, and using all the things that you've already learned about normal models, you can find a lot of probabilities with those. So, yeah, that's it. Thanks for watching.